Welcome, everybody, officially. So glad to have you with us this afternoon for the first of our fall series in the EdWeb Building Understanding in Mathematics community. I'm Sarah Delano Moore. I'm your hostess in the community and lead the webinars. We're thrilled that all of you are with us. Please continue to say hello in the chat and talk amongst yourselves as you do. There's always such good conversation there for us as well. Our session here is part of, our series here is part of the Building Understanding in Mathematics community at EdWeb. That community is sponsored by ETA Hand to Mind. And when you join the community, you'll get invitations and information about upcoming webinars. You'll get easy access to the recordings and the resources that are there. Continuing education quizzes, if you're on the phone or watching the recording, that will be important. And then the online discussion forum as well. So we'd love to have you join us there and continue to join us in the webinars, either live or by recording, depending on what fits your schedule. We've got some folks from all over with us today, so some are up late at night and some of our West Coast friends have trouble getting in because school's not out yet. If you're logged in live on your computer with your email address, your continuing education certificate will come tomorrow by email. If you're on the phone, you'll need to go to the web and take the quiz in the archive section. Or if you're watching the recording, you'll want to take the quiz in the archive section in order to get your certificate. The phone doesn't know who you are, so we're glad you're with us that way. Just have an extra step we need you to take for that. I am your hostess, Sarah Delano Moore, and you can learn more about me if you want to read this later, but I'd rather get doing math, so I tend to skip over that part. As I said, our community is sponsored by ETA Hand to Mind. Our work today is really going to feature base 10 blocks as one of our manipulative tools. And so if that's something you have in your classroom, I hope this is an incentive to pull them out and use them. If that's something you don't have in your classroom yet, I would encourage you to work on finding the resources to get some, because they really are a powerful tool for helping kids think about and make sense of adding whole numbers and decimals, which is our focus today. Our theme for the fall is this idea of building bridges from concrete to abstract. We talk so much in this community about how do we use manipulatives to teach mathematics? How do we do hands-on learning? Why does hands-on learning matter? What does that look like? And we tend to stop in the community here. We tend to stop in the community here at the point of we've built the manipulative models, we've maybe drawn some pictures, and we leave it that the rest of the work, the abstract, will come. We decided for this fall we wanted to focus our work on how do we move all the way to the abstract. And so we're really going to be thinking about how do we help kids make sense of algorithms and what's going on in algorithms based on the work that they can do with manipulatives, and how do we close that loop, build that bridge all the way across. We're starting today with addition and subtraction of whole numbers and decimals. In October, we'll talk about multiplying and dividing whole numbers. And then in November and December, we'll look at fractions, and decimal multiplication and division we're going to pick back up in December because there's a lot about it that behaves like fractions. So you see decimal split because I'm trying to keep it sort of where things behave most nicely. And that's the nature of the beast. That's the way decimals work. It works pretty well because typically we teach decimals later and kids have that foundation. For today, we're just going to combine the add subtract with decimals with the add subtract with whole numbers as part of what we do. 72%. Why does it matter? This statistic, this number, comes from a research study looking at the impact of using manipulatives on student achievement. The researchers analyzed data from NAEP, from the National Assessments of Educational Progress. And what they found was that in classrooms where students use manipulatives on a weekly basis, student scores on NAEP were about 3/4 of a grade level, 72% to be exact, about 3/4 of a grade level ahead of students from classrooms where manipulatives were used on a monthly basis. This is work. This kind of teaching that we're talking about in this community, this idea of using hands-on tools to build understanding, is work for teachers. I share this stat, I start the series with this stat, because this to me says the work is worth it. It's not that if you take the lid off the manipulatives box once a week, you're going to see your test scores go up by 3/4 of a grade level. It's that when you take the lid off the manipulatives once a week, you're going to change the conversations that are happening in your classroom. You're going to move kids to a way of doing math that makes it make sense, so they can answer the question why, or they can show you how these two representations connect, or they know what it means when they do X or Y or Z. I was saying before we got started, I've spent the last few days in schools in Tennessee and Western North Carolina. And part of what I've been reminded of the end of last week and the first part of this week is how important this sense-making work is. Because I've seen middle schoolers who can simplify a fraction because they know a magical way of counting on their fingers. But I ask them what that means, and they don't know how to answer. We're working on teaching here that will let them know how to answer that question. And this idea that the kind of conversation we have, the kind of thinking we have that comes from working with manipulatives, that's what leads to 72% gains. And that has great power. So as I talk about the work of this, I always like to remind us, why does it matter? When we teach with manipulatives, the evidence tells us that manipulatives provide support for student learning when teachers help students build links between the object, the concrete, the symbols, the pictures, the representational things, and the abstract mathematical ideas. That comes from a report called Adding It Up. And again, it's the more research literature part of why this matters, how we do it. Our focus in this series is, what does it take to build the links between the objects, in this case, the base 10 block, and the abstract, in these cases, the algorithms. That's what we're thinking about. So our questions for the day, for the series really. How do we connect these concrete objects with the abstract, the symbols and procedures we use? How do we then make those connections visible to kids and use manipulatives to help the algorithms make more sense? I keep using this word algorithm. The algorithms are the standard grown-up way we do this. Add these two numbers, put this down here, carry this over there, regroup it here, put in a zero, move over. All that Charlie Brown teacher that we talk about. I want us to put this in the context of what the standards tell us. When we talk about moving towards the standard algorithm, what we're talking about is becoming efficient at multi-digit computation. Efficient doesn't mean fast, it means fast enough. Efficient doesn't mean I can do 12 digits plus 12 digits or 10 digits times 8 digits quickly. In my calculator right sometimes. But up to 5 or 6 digits, can you do it by hand? And can you do it well? Can you do it fast enough and accurately enough? But use strategies, know what it means. The way the standards are typically structured, and it varies a bit from state to state across the US, and our global friends, it will vary in your communities as well, perhaps, but the general progression is that first we have kids figuring out efficient, accurate, generalizable methods based on place value, based on properties of operations, things like that. Then we start to say, how does this written method work? What's going on? How do I use this visual model to explain what's happening in this written model? Then I want to move kids towards a standard algorithm without the visual model. They may still be seeing it in their heads. Depending on how your community does high-stakes assessment, often teachers have to cover up or take down posters and signs that have been going on, that have been in the classroom, you see kids looking at that space even without the sign being there. They'll keep that visual model in their head. Pia, I see as a question, yes, the recording will be available later. Sorry you're having audio trouble. Standard algorithms typically talk about decomposing numbers into base 10 units. We'll look at what that means a little bit later with some examples. And then we can use single-digit computation methods over and over and over and over again through those places. They take advantage of the consistency of base 10 structure to generalize. So when do we have to do this? You'd be surprised. In first grade in much of the US, we're adding and subtracting within 100. Like with like, we might be composing tens a little bit. Second grade, we're pretty fluent within 100. We're working with concrete models and strategies within 1,000, so kids can see that what I did as I moved from ones to tens, I do again as I move from tens to hundreds, that iterative nature of the process. Third grade, we can use strategies and algorithms within 1,000. Haven't had do the algorithms from memory yet. That comes in fourth grade for adding and subtracting multi-digit whole numbers. So much of the work I'm talking about today is what will be happening in classrooms in grades 2, 3, and 4 as we move kids through the later part of this progression. Then in grade 5, I'm working with multi-digit whole numbers and decimals to hundredths. And then in grade 6, now I'm fluent with multi-digit decimals. It's not until grade 6 that we say, put any numbers down there and add or subtract them. I start here because I want to remind you that we have some time. One of the ways we've gotten in trouble in the past is we were teaching these algorithms without any conceptual foundation, and we ask kids to memorize them. And it's hard to remember it if you don't have a foundation for it. So we're taking time in these standards to build that foundation. Again, depending on your state or your country, because we've got folks with us from all over, it may vary a little bit. But this general progression will apply across much of the US at least. And the thing to remember is you have some time. So let's start to explore what multi-digit addition looks like. I have a problem up on the screen for us. We're going to spend a lot of time with this problem. 348, add 175, and that's the same as 523. I mentioned at the beginning, one of the exciting things about today's session is we're going to try screen sharing again. It's been a while since we've been able to do that at EdWeb, and we are thrilled to bits that it is back. I'm going to change now so that you all are seeing my desktop. And I'm going to minimize this. And let's do some math. Because after all, that's why we're here, isn't it? The first strategy I want us to think about is the idea of counting on. We start counting on when we add 6, add 3 more. 6, let me get it in the camera, 7, 8, 9. That's counting on. I'm looking here at how do I use counting on with base 10 blocks for working with a larger number. So 348, I've already built that on the screen, and you can see it. If I add 100, I'm going to pull in another flat. And so if I want to keep a running record over here on the right, 348 plus 100 more is 448. Continue counting on. Oop, grab it here. I'm out of practice. I'm going to add 70 more. Here we go. At this point, the value of what's on my mat, and kids would have physical base 10 blocks in front of them, clearly. But for our purposes today, we work with the visual version. What I have on the mat sums to 518. It's a little messy. I got a whole slew of rods on there, don't I? So if I want to rearrange and clean up a little bit, here's 7 of them, 8, 9. Let's get those 10 out of the way and trade it. Now it looks a little more like 518, doesn't it? Now I'm going to bring in my last 5. 523. Again, because I have too many units over here. Typically, I don't want more than 9 in that space. There's 5 of them. 6, 7, 8, 9. I'll get those 10 out of the way. Trade it for another rod. Here's my 523. I've built this as a physical model so you can see what's happening. But this is a strategy children can also use as mental math. 348, that's 448. 448 plus 70, 44 plus 7 is 51, so 518. 5 more takes me to 523. This is the beginning of what happens in the standard algorithm, and so we want kids in grade 2 and grade 3 to really think about what does this look like and how does it behave. Then we can ask them to get a little more abstract and think about the same model on the number line. Judith, you asked a great question. Let me come back a slide. One of the things we talk to young children about, Judith's question is why wouldn't I start with the ones? Typically when we're counting on, we think about count. So for my kindergarten example from earlier where I had 6 plus 3, typically we would encourage kids to start with 6 and then add 3 more rather than start with 3 and add 6 more. Just depends, but that's what we would think about it. If they can't mentally add 448 plus 70, you heard me pause at 44 plus 7, just add the 10s. That one might be simpler. But our typical model with counting on is start with the big stuff and keep going. I see a suggestion in the comments about money, and that's certainly another way to help kids think about this. This is a scale where we could be talking about 348. Let's look at the number line version and see how that works. Oh, Pia's got another good idea. I like that. So let me grab a pen. And let's see how this is working. If I have 348, I'm going to jump by 100. And now I'm at 448. Pia's suggestion was jump by another 100 to 548. And then, let me change color, jump back 25 to 523. 175 is almost 200. And it's a pretty friendly distance from 200. So let me go ahead, jump ahead 200. I did it in 2 hops. and then come back 25. That's another way to think about it. It's another way to see what's happening here and consider how this might be working. Third and fourth grade students, Mohammed, will understand this way of working on the number line if they started doing this with smaller numbers. Let me clear my mat. And pardon me, I'm going to have to just scratch some stuff out. Let's pretend we had 17 and we want to add 25. 17 plus 10 is 27. Plus 10 more is 37. Plus 5 more is 42. That's one way to approach it. Another way to approach it, let me change colors, is to say 17 plus 3 more is 20. Some of you are talking about landmark numbers and friendly numbers. Now, what I just did here, I added the 3. How much of my 25 do I have left? I have 22 left. So 20 plus 22 is 42. If I've had these experiences, then thinking about how to work with larger numbers like I started with makes more sense. And students get very comfortable with it. I wouldn't make the problem I have on the screen, my main 348 plus 175, the first problem kids ever see this way. Even if you're working with older students, go back to smaller numbers. Talk about benchmarks and friendly numbers. And you can, as Jason's rightly saying, I didn't choose to put both images on the screen. But if I open this up, I don't think I can make that any bigger. You start to see how this image and the pieces we did up here at the top matches. When I pulled in that flat, that was my plus 100. When I pulled in those 7, that's my plus 70. And Jason's comment about in the same line of sight. Model, model, model. P is a woman after my own heart. Let me clean my screen up a little bit because I'm trying to keep it friendly for you guys. So that's the notion, and that's one way kids move towards algorithms, is this idea of counting on and extending that strategy from early up even to these larger numbers. That's going to help us with the other way of thinking, and that's about grouping based 10 units. You are so right, I think it's Julie, that part of what's scary about this for teachers is that they weren't taught this way. What's cool about it, if you can take a deep breath and talk to your colleagues and watch webinars like this and take the risk to try it, is they'll see their kids blossom when they give them a chance. And that's so energizing and so exciting. So here, same problem. Let's think about it, though, not as counting on, but as grouping our base 10 units, like with like, because this is what's going to get us all the way to the algorithm, all the way to our approach. So I've already built 348. I'm trying to minimize how much you have to see me drag in. And now I'm going to go ahead and build my 175. I can build in any order I want. I tend to build in the same order I read the number. So here in yellow is my 175. And now I'm going to think about What is it I have here? I have 400s. I have 11 tens or 100 tens. I have 13 ones. I can do some regrouping. I can do some rearranging. We are going to talk a little bit about where we go with decimals. Decimals are easy if we have this good foundation. So I can say, all right, instead of 13 ones, here's 8, 9, 10. That's going to become another 10. Here's 7, 8, 9, 10 longs. That's going to become, so this is now 3. This is now 20. I just made another flat for over here. Forgive me, I'm out of practice drawing squares. There's my 523. Kind of messy here, but let's look at it again like this, where we were talking before. We have everything in one line of sight. We have everything together. This is about giving kids a strong foundation in number sense. That's really what this is about. I think that's such an important comment. Is it Sarah? The print small on my iPad where I'm reading chat. So let's think about what happens here. I have 8 ones and 5 more ones, and 5 and 8 is 13. Do you remember partial products from multiplication? This is partial sums. Same basic idea. I have 4 tens and 7 more tens. That's 11 tens or 110. I have 300s and 1 more 100. That's 400. Add those partial sums. I get 523. I didn't color code this. Probably should have. 8 plus 5 is 13. 4 and 7, 4 tens and 7 tens is 11 tens or 110. Three hundreds, 100, it's 400s. What I've done is reduced this big multi-unit, multi-digit addition problem to a series of single-digit problems. 5 plus 8 is 13. I've known that since first grade. 4 plus 7 is 11. I'm adding to that my place value understanding that that's not 4 plus 7. It's 40 plus 70, or 4 tens plus 7 tens. And that's 110. Partial sums could be great with an expanded format, an expanded form idea. And again, over here, I drew this in sort of a messy way before, but here's how I would sketch. So I have the concrete in the base 10 blocks that we build with on our desk. I have the sketches like this that I would make to be visual representations. And now I'm moving more and more towards the algorithm. If kids can do this partial sums, they can learn to shorten it to be the algorithm. So let's jump over one more screen. I kept to largely the same example because I can't keep it all in your line of sight at one time. Let me grab a pen again. Now I'm going to get to what my teacher did in school, but it's going to mean something to me. 5 plus 8 is 13. That's a 3, 3 ones and a 10. 7 plus 4 is 11, one more is 12. Tens, so that's 2 tens and 100 from that other 10 of them. 3, 4, 5. For some students, they lose track of these guys up here at the top. So let's try it a different way, just a different way of writing it. 5 and 8 is 13. 4 and 7 is 11, and one more is 12. 3, 4, 5. I wrote my regrouping at the bottom. I have to really stop to think to write 13 as 1, 3 rather than 3, 1. I struggle with that because my habit is so deeply ingrained for the first way I showed you. These ideas pair beautifully with number talks. They really, really pair nicely. I missed who, sorry about that. But somebody talked about that in chat, and it's a really powerful idea. This is how, when I work through a sequence like this is how I see that this algorithm makes sense. It's not just doing what my teacher told me. And I would raise my hand right there and say, I learned to do this because my teacher told me to. And they told me I was good at math because I could remember. And it wasn't until I was an adult and had a moment of horror when one of my students said, why? And I had the presence of mind to answer, I don't know, but I'll go find out. And 20 years later, I've found some stuff out. And for all of us, it's that progression. It's that thinking. Now, if we know this, and I'm in 4th grade right now, and I ought to be able to do this with bigger numbers, but I'm not going to make you watch me do it in bigger numbers. Try it for yourself. Then moving to decimals is really not hard because it's still like with like. Thanks for sticking with us, Brian. It's still like with like. So what changes about decimals is that not only am I adding the tens and the ones, but I also have to add the tenths, the hundredths, the thousandths. So you see here on the left, I went ahead and added, using that partial sums method again, 7 thousandths and 5 more thousandths is 12 thousandths. 5 hundredths and 8 hundredths is 13 hundredths. 4 tenths and 1 tenth is 5 tenths. 23 and 4 is 27. I chose to chunk that one. All of my parts about lining up the decimal points, that's still important, but it's not just a theatrical line up the dots. If I line up the decimal points, then everything in this column is a 1. And everything in this column is a thousandth. And so forth and so on for the columns in the middle. It's that same idea. It has to have meaning. That can't be a 7 and a 5. It has to be 7 thousandths and 5 thousandths. Make 12 thousandths. It's painful for me to talk that way. It's not anymore, but it took a lot of work at first. And I still mess it up sometimes. So now I want to think about shorthand again. 7 and 5 is 12 thousandths. 5 and 8 is 13, so that's 14 thousandths. 4 and 1 is 5 and 1 is 6. Decimal point comes along because it helps me keep this together, and 23 plus 4 is 27. Using graph paper or turn your notebook paper sideways so the lines make columns are great strategies for helping kids with the mechanics of lining up the decimal point. What's critical is I want them to understand that I'm lining up the decimal point not to please my teacher, but because it means I'm continuing to add like with like, just like I always did. See, if I go back, the decimal points were lined up. We just didn't bother to write them because we don't know anything yet about numbers to the right of them. Joan, your comment about teaching diverse learners and the more ways you can present things, that's where the gain in achievement from teaching with manipulatives comes from. It's that I catch more kids. Think about what we've done. We've talked about counting on. We've talked about combining like with like. I didn't say it earlier, but I'll jump back and say it now. When I'm adding here, I can add in any order I want. I can see what's happening no matter how I do it. That'll be even more true when we think about subtraction in a minute. And you're right, this is about combining like terms no differently than in algebra class. How many times have we talked in this community over the years about we're getting them ready for algebra? And as I said earlier, I've been in these middle and high school classrooms lately where I'm seeing kids who've had this kind of background, and it makes such a difference compared to those who haven't. So I am going to switch us back to the PowerPoint. Pardon me while I pay attention and click a couple of times. And our friend Regina is going to reload the presentation for us so that we'll see those slides again. There we are. And like magic, we are right back where we left off. So we've been thinking for the last 25 minutes or so about addition and really developing from the kinds of multi-digit strategies we might use, like counting on or working with base 10 blocks that continue from what primary kids do. I've stayed, like I said, largely in the realm of grades 3, 4, and 5. But you can see, and you all have been talking in the chat about the fact that kids need this from the beginning. If I hand this to a 5th grader who's never seen any of this, it's going to be rough. But if I can work vertically, get that continuity in my school to build these senses, I can really help them think about what's happening. Now for the second part of our session, the last part, these last 20 minutes or so, I want us to think about subtraction. We're going to work with a couple different problems here. But you'll see that we are doing very similar things and using similar models. That's intentional. Kathy asks a question about the place value discs. I find the place value discs really useful for working with larger numbers, particularly beyond 4 digits, where kids need a physical object. You know, it's not practical to do 5 and 6 digit numbers with base 10 blocks. What the discs do not do is show kids the proportionality. Yeah, Julie's phrasing it as conceptual space. The discs don't help me know that 100 is 10 times bigger than a 10. So I want to do work with base 10 blocks first, and I want kids really comfortable with base 10 blocks. The discs occupy a little space, they're a little easier, but be careful about sequencing them when you use them. Coins, oh, Jason, don't even start on coins. I'll only talk about American money. I know we have lots of folks from all over the globe with us today, but what is it about a dime that's more than a nickel? It's smaller, it's thinner, it's lighter, it's everything less except its value. Coins are messy. You can use base 10 blocks for decimals. I don't remember when, but if you check the archives, you'll see some sessions where we've done that over the last couple of years. The thing you have to be careful about is that the name of the base 10 blocks piece is a flat. Today, I'm giving that flat a value of 100. Today, I'm giving that flat a value of 1. If I've named it flat all the way through, it's easier. If they thought of it as 100 and now all of a sudden I'm saying, wave my magic wand, it's 1. That's tough. So it needs to be part of that vertical progression to make it work. I talked about counting on for addition. So we're going to think about counting back now for subtraction. 751 minus 548 is the same as or equal to 203. 751. I can take a giant jump back of 500. I could go 100 at a time. But I could take a giant jump back of 500. And you see that those 5 flats have moved out of the way. And now I'm at 251. I can do another jump of 40. And now I'm at 211. I've got to do some trading. I couldn't take 8 away, could I? But if instead of saying 110 and 1 I'm going to have 11 ones, now I can take 8 away, and I'm left with 203. Same idea, just working backwards instead of forwards. If I want to, I can also think about a missing add-in problem, because remember, addition and subtraction are related. Brian, that idea of jumping in tens or multiples of 10 comes from the fact that early in learning to add and subtract, the first thing we teach kids to do is add and subtract multiples of 10, so that they're really only working in one place value slot at a time. So I don't know that I would go so far as to say it's innate, but I think it is something that we work with a lot because it takes advantage of making it easy. If I add 100 or subtract 100, I only have to change that one digit, and that's helpful. So now my problem becomes 548 plus what will get me to 751? How do I jump? And I can think, all right, I could jump 100. I could jump 200. That takes me to 748. 3 more will take me to 751. The cool thing about this strategy is I've shown you on the screen the efficient way. If you had a child who wanted to only jump in tens, it would take a little while, but they could do it. It would just take them 20 jumps of 10 to do that 200. And then you could challenge, can you do it in fewer jumps? What's the smallest number of jumps you could do it in? And encourage them, move them towards this kind of bigger chunk thinking. Some kids might say, I want to jump 52 the first time because that's going to get me to 600. It is skip counting, Brian, exactly. Those things don't go away just because we left second grade. So I might take 548, I'm going to add 52, that gets me to 600, then it's another 151. Exactly. There are lots of ways of thinking about this. There's a lot of flexibility and fluidity in this work. The thing I want you to be careful of is no run-ons are allowed. Sometimes when we write this, we have a tendency to write 548 plus 200 is 748 plus 3 is 751. But 548 plus 200 is not the same as 751. That's why my little red no signs are in there. If I want to think about decomposing base 10, you're going to start to see some screenshots now from a virtual manipulative resource called Braining Camp. That's a newer partnership for Hand to Mind and another way of approaching the virtual manipulatives beyond the Active Inspire tool that I was using at the beginning. So we're going to try in the next session or two to go live to some of this, but for today, we decided to work it this way. So you'll see some screenshots and some math on the side, that idea of keeping two models in view at one time. So if I want to subtract, this problem is 421 subtract 156. And if I want to subtract here, I can do that by doing all of my regrouping at once. That's one choice. So here I've regrouped from 400s to 3 and from 2 10s to 12 10s. And then I can look over there and say, but I'm not going to be able to subtract 6 from 1, so I'm going to regroup one more time. So now I have 3 flats, 3 hundredths. I have 11 rods or longs, 11 tens, and I have 11 ones. That still has a value of 421. Lisa's excited about run-ons. It's such a big deal. The cool thing about this is I can subtract from left to right if I want to, or from right to left, or I can start in the middle. It doesn't matter because I'm working with place value. And so when I do my subtraction, when I pull things out of the way, 300s remove 100. 11 ones remove 6 ones. 11 tens remove 5 tens. I'm left with 165. The other way to think about this is that I can alternate regrouping and subtraction. And this is what most of us were taught. So I look and I say, I'm going to start with the ones. Can I subtract 6 ones from 1 1? Not easily. We don't know about negative numbers yet. So I need to regroup. I need to trade one of my 10s for 10 ones. And you can see I've indicated some of the notation of the algorithm here. Having both in the same place helps kids see what's happening. When I change that 2 to a 1 in the tens place, that's because I'm going from 2 tens to 1 10, and I'm going from 1 1 to 11 ones. And now I can take 6 of them away, and I have 5 left. So now I have 1 10, and I need to take away 5 tens. That's a problem. Brian, please tell me you're not getting loster and loster, because we want to catch up. So I can't take 5 tens away from 1. So I'm going to do another trade. Instead of 400s, now I have 300s. I have 11 tens, and I can take 5 away, and now I have 6. $300s take away 100, I can do that. I apparently forgot to move it on the screenshot, forgive me, but it can be done. And so my difference is 165. There are a lot of steps here. There's a lot going on. And the challenge of EdWeb is always that we have an hour. It is 265. Thank you, Karen. You get bonus points. We'll fix it. Oh, Carlene does too. See, this is what we get. There's always something. Thank you, guys. Bonus points to all who caught the teacher in a mistake. We've really got to think, though. It is exactly, Tracy, and this teacher needs correction sometimes, so I'm grateful. I had it right at the top of the screen, just not at the bottom. So we need to think about, what does it mean? Those of you who are in other parts of the world, you may have slightly different language for this. Mistakes are how we learn. Thank you, John and Patricia. You may have slightly different language for some of this. You're going to want to connect it together. But you can see what we're doing. We're showing how all the squiggles that we were taught to write actually have meaning in the mathematics. So now if I think about decimals, I can do a similar sort of thing. I can count back. Same strategies will work. 2 and 32 hundredths, take away 1 and 68 hundredths, equals 64 hundredths. 2 and 32 hundredths, take away 1. That gets me to 1 and 32 hundredths. 1 and 32 hundredths, take away 6 tenths. I might take away 3 tenths to get to the friendly number of 1. We've been talking about different choices. I chose in the slides to keep my hops the actual place value of the number I'm subtracting, because I wanted to make that connection. I encourage you, all of you, to help your kids think about, how many different ways can I get there? And what makes some ways easier for me than others? Take away that last 8 hundredths, and I'm left at 64 hundredths. On the right, I can regroup. And I can decompose my base 10 units. Here, let me go back. I'm using my flat for a whole. Somebody was asking earlier about using the base 10 blocks for decimals. I've done it here. 2 wholes, 3 tenths, 2 hundredths. I can't subtract. So I'm going to rearrange and do some regrouping. I'm going to swap one of those flats, 1 whole, for 10 tenths. It gives me more stuff to move around and take away. Exactly. I'm going to swap one of those tenths for some hundredths. And now I can subtract from left to right, right to left, whichever way I would like. Take away 1 whole, take away 6 tenths, take away 8 hundredths, and I'm left with 64 hundredths. Regrouping gives you enough that you can take away what you need to take away. That's exactly why we do it. And when we do that, we're going all the way back to that first grade physical model, even kindergarten, physical model of subtraction as takeaway. I need to be able to lift these pieces off. I need to be able to take them out. I need to be able to count backwards. The number line's more abstract. Oh, now Eric's getting fancy. Adding 32 hundredths to both. He's shifting the whole problem on the number line. That could be a whole nother webinar, Eric. At 3 minutes until we're done, you get bonus points too for raising that, because that really is a cool strategy and a cool approach. It's another way to get to friendly numbers. The key thing here for any of these models is that children are never writing down numbers and crossing things out and changing them and adding them and all of that stuff that is part of the standard algorithm without being able to say, this is what it means. This is why we do this. This is what's happening. And if I can see what's happening on a small scale, then as I get to numbers at the extreme, larger and larger whole numbers, smaller and smaller decimal pieces, I trust that it's still going to work because I understand enough about base 10, 10 times bigger as I move to the left, 10 times smaller as I move to the right. I think I said that the right way. You know what I meant. I trust that it's going to work. So this is the kind of experience we need as teachers to give kids, to give the teachers with whom we work, so they can help us think about what's happening and teach these algorithms as efficient sense-making tools, not as do what I say, copy it a lot, please don't ask why. I got in trouble for asking why. I don't know about you all. And I don't want to be in a classroom like that anymore. My teacher was doing the best she could, I know that. But I don't want kids in classrooms like that anymore. And so we have to think about this and do this work. So I am so pleased that all of you were able to be with us today and think about this. Thanks, as always, for your contributions in the chat. We're always grateful for that and glad you're joining us. We'll be back together in about a month to talk about multiplication and division of whole numbers. And then later on in the fall, we'll move on to fractions. Your continuing ed certificate will come by email in the next day or so. If you're on the phone or the recording, remember that you need to go take the quiz in the archive page. We're going to use fraction towers or fraction bars for the fractions. So we'll use manipulatives, but not the base 10 blocks when we get to fractions. I'm always glad to be part of the community and grateful to you all for hosting me. And we are so pleased that ETA Hand to Mind has sponsored all of these webinars over the years, and so glad to be part of this community and have them supporting us in the world of hands-on learning. We've got all the dates up here and look forward to seeing you again over the fall. Thanks as always for joining us, everybody.